In this video, we'll look at a couple of lemmas or facts about circles, properties of circles, and then we'll prove one of them. Okay, so let's see if we can figure out what goes in this blank here. The center O, we have a circle, and we have the center O, is the blank of any diameter. Remember what a diameter is. It's just a line segment from one point to another point that goes through the origin. Well, what's special about that point? Well, it happens to be the midpoint of any diameter. So the circle, the center O, is the midpoint of any diameter. So this length is the same as that length, two equal lengths. The next one is the perpendicular bisector of any chord. So let's make a chord. Maybe I'll go from here to there. That's a chord. The perpendicular bisector means you go to the middle and then you do a 90-degree angle, or orthogonal, perpendicular here, 90-degree angle. That's going to pass through the origin. The perpendicular bisector of every single chord will pass through O, the origin. I'll go ahead and say the origin O. All right, third one. Any segment joining O to the midpoint of a chord, well, you might guess 2 and 3 are very similar. Any segment joining the center O to the midpoint of a chord, here's one example, is perpendicular to the chord. So again, those two are very similar. All right, the last one, 4, we're going to state and prove at least part of it. It says 2 chords are equidistant from the center O. This double arrow means if and only if the 2 chords are congruent, which means they have the same length. All right, so this proof is going to be 2 cases. You have to prove that direction, and you have to prove that direction as well. So it looks like the proof of this one is going to be left as a homework problem. That will be if 2 chords are congruent, then they are both equidistant, the same distance from the center. What we're going to prove is the arrow going this way. Assume we have 2 chords that are equidistant from the origin, and we will prove that those 2 chords are congruent. They have equal length. All right, so I've already started the proof for us here. It says, okay, again, we're assuming the left part is true. Assume that chords, and I named them A, B, and C, D, are equidistant from the center. And then what we'll have to prove is the right side, that the 2 are congruent. This means they are congruent. Another way of writing that would be the chord is congruent to the chord AB, or line segment AB. These mean the same thing. Same length. All right, in the picture I already drew the 2 chords A, B, and C, D, and the picture may not look exactly right. I just estimated them. I tried to make the chords exactly the same. This one looks a little bit shorter, but we'll just pretend like they're the same length. You don't trust pictures anyways. Okay, so step 1, drop perpendiculars from O to both of those line segments. Okay, both of those chords. Remember, perpendiculars, another way of saying it is it's a shortest distance from the point to that line or line segment. So we've got that and we've got that. Okay. So we drop the perpendicular from O to AB, from O to AB, and we're going to call, oh, this is O, and AB, and it says call it X. We're dropping the perpendicular to that point X, and we're dropping this perpendicular to the point Y. Okay, well, next, we know that OX is equal to OY. Why? Because, let's see, OX and OY, let's see, we're assuming that the chords are equidistant. This is the distance from the point to there, the distance from there to there. So we're given, I'm just going to put our justification for that is we're given that that is the case. Okay, now OB, I'm going to draw these line segments. OB, OA, OC, OD all have the same length. That should be obvious. The reason for that is each one of those is a radius of the same circle. So I'll say all radii, that's the plural of radius, all radii of same circle. Therefore, they all have the same length. So let's make a notation that, let's see, I'll put 2 through them. Those all have the same length. All right, so that tells us the next thing I'm going to write is the triangle AOX is congruent to triangle COY. COY. Okay, let's see. What is the reason for that? Well, we could use 2 different justifications. They're both right triangles, here and here. So we could use either the HL, hypotenuse leg. They've got the same length of hypotenuse and the other leg, and then they have the 90-degree angle. Or we could just call it side, let's see, side, let's see, what do we have? Side angle. We could use that special side angle, but I'm going to go ahead and call it the HL. It's a right triangle, same hypotenuse, and one other leg is the same. So that's the reason those 2 triangles are congruent. And then after that, I'm going to say CY is equal to AX, which means the line segment CY has the same length as AX, which if I wanted to then I could put 3 notches in it. And the justification for that is we have 2 congruent triangles. So what do we usually write? We usually write corresponding parts of congruent figures are congruent. Okay, notice I indented that a little bit. I'm going to write 2 more lines that are very similar to these right here. Okay, so notice that triangle BOX is congruent to triangle DOY for the same reason above. We've got a right triangle, the hypotenuse, and another leg, and we call that the HL, hypotenuse leg. And then we've got, because of that, we have that XB the length of that segment, is equal to yd, the length of this segment. yd and xb. So I could put, well, I'm just going to put 3. Because we'll find out that all of these with 3 notches have the same length. So I'm going to say that again, that's by corresponding parts of congruent figures are congruent. So to finish this off, by, I'm going to call this 1 and 2. By 1 and 2, we see the following. CD, which is equal to, notice that CD is CY plus YD. All right, that's CD, and that's equal to, let's see, AX plus XB, AX plus XB, because AX is equal to CY, up by number 1, and YD is equal to XB by number 2. And what is another way of saying AX plus XB? That's the distance from A to B. And therefore, this is exactly what we wanted to prove. CD, the distance from C to D, is the same as the distance from A to B. CD is equal to that, which is equal to that, which is equal to AB. So maybe I'll conclude it with, so CD equals AB, and that's exactly what we needed to prove.